Right, our opening speaker is Arun Ram from University of Melbourne. He'll be talking about are there symmetric group crystals.
Thank you. Great, thank you. Well, it's a pleasure to be here, absolutely. It's a pleasure to see such so many old friends and actually new friends too. I noticed that half of the people came from Sydney, so it wasn't actually such a long flight from Sydney, less than 10 hours. But I want to thank the organizers for having me come, and I also want to thank you for allowing me to speak first so that I can party afterwards. All right, so last week we had this conference in Sydney, and one of the things that we were supposed to do, I think Jordy was insisting that we talk about future directions. And I didn't cooperate so much, a little bit, but today I really am going to cooperate in the future directions thing. So this story is about Kronecker products. So let me just, I'm sure that everybody here knows what the Kronecker problem is, but let me just write it because it'll help to set some notation. So Sn lambda is the simple CSN module, just simple characteristic 0. So it's indexed by a partition lambda, which I will write as lambda 1 greater than or equal to lambda 2, etc., with lambda I non-negative integers, and the sum of them is n. And the problem is compute, in some way, gamma mu nu lambda, where gamma mu nu lambda, where you take the Sn mu, tensor Sn nu, and that's isomorphic to, that decomposes as a direct sum over lambda of Sn lambda, where that appears gamma mu nu lambda number of times. So everybody knows this problem. Compute the decomposition of the tensor products of the representations of the symmetric group. So of course, I like to tell this, now I'm going to tell this story, and I like to tell the story this way, which is more or less accurate, but pretend that we've all been to the pub in advance. So this is a problem which, of course, you meet, I don't know, in your second week of representation theory class or something. And you start asking around, well, what's known about this problem? And everyone says, oh, well, it's hard. It's been known since Frobenius or whatever. And so this happened to me when I was in graduate school, and I looked at it a little bit, and I looked at what was sort of known up to that time. I sort of learned what Littlewood did, a little bit about Murnaghan. I learned what Garcia Reynolds sort of rewrote Littlewood using algebraic combinatoric techniques from the 80s, from the Stanley School. And then I said, well, okay, I don't have any good idea after that. So I'm not going to work on it because there was this little thing about getting a job and then getting another job. And so you don't work on the Kronecker problem unless you have some idea. So then I noticed, recently there's been a little bit of activity around this. I see people in the audience, Chris Bowman and so on. And I didn't really, I have to admit, I didn't really pay attention. I sort of got the paper and I skimmed it. And this February, I was in Paris at the IHP for a wonderful program. And I got to Paris, and you go to tea. One of the wonderful things about this program is you go to tea. And the first day, somebody came up to me, I think it was Greta Panova, and asked me, so what do you know about the Kronecker problem? And I said, I don't know anything about the Kronecker problem. Does anyone know anything? I said, well, years ago I studied Littlewood and Murnaghan, and I don't know that I've learned anything since then. Of course, I haven't looked at it since then either. And then the next day, somebody else came up to me. I think it was Ernesto Vallejo. What do you know about the Kronecker problem? I said, I don't know anything. Do you know anything? So this happened day after day, 4 or 5 times. okay, so fine. I was busy doing my own work. But then there was this wonderful party in the Zemlitsky Tower in Jussieu, way up on the 15th floor where you can see all of Paris, and there was wine and food and all this. And of course, that's the problem with me. Once there's stuff like that, I start drinking wine. And somebody came up to me and said, look, do you know about this Chronicle problem? I said, what's going on? Everybody wants to know, did something happen? Did I miss it? What's going on? So I said, what do you know? Tell me. And so then, of course, I'd had too much to drink, so I said, well, come on, look. If you want to solve the Kronecker problem, let's just look at what tensor product problems have ever been solved. And then, as far as I know, there's only one that's been solved, and that's the Littlewood-Richardson rule. One sort of general problem, Richardson rule. And that's a problem about ln lambda, the simple GLN module, GLNC module. Now, lambda is also a partition, but with slightly different constraints. So lambda I are non-negative integers, and lambda n plus 1 is 0. And then you want to compute, again, these C mu nu lambda, where you take the tensor product of ln mu with ln nu, and that decomposes as a direct sum over lambda of ln lambda appearing C mu nu lambda times. And that's called the Littlewood-Richardson coefficient. So I said, okay, how did we solve that? And it's very interesting. You can replace GLN by a reductive group, a complex reductive group G. And ask the same question. And that one we did solve. And I said, how did we solve that? Well, we solved that by crystals. So all the proofs that I know are you let Bn lambda be the crystal corresponding to lambda, to ln lambda. And then the solution to the problem is C mu nu lambda is equal to the number of connected components of highest weight lambda, in the labeled graph. So there's a labeled graph, which is Bn mu tensor Bn nu. And so then I said, that's the only one I know how to solve. And all the proofs of Littlewood-Richardson rule that I know, at the end, they're pretty close to crystals. It's pretty hard to get away from, even though if you try not to say crystals, you're still more or less using Shenstedt or something that's crystal theoretic. So I said, if you're really serious about solving this Kronecker problem, find me a theory of symmetric group crystals. Okay, so that was the end of the conversation. We had more to drink. So the next day at tea, somebody comes up to me and says, so what's a crystal? I said, I have no idea what a symmetric group crystal is. I can tell you what a GLN crystal is, but I never thought about it. Next day at tea, somebody else comes up to me. So what's a crystal? I have no idea. So finally, I started to think about what is a symmetric group crystal? What could it be? So maybe I'll start to use the slides. I did, because I want to show pictures, I did prepare some slides, but I'm not good with the timing when I use slides, so I'll do the best I can. So this is the Kronecker problem. We've already read. Yeah.
Is your concept different from normally the quantum group construction? Do you have your own idea?
Well, I don't know a quantum symmetric group. I mean, I know the heck out. What?
So normally wrote a paper on quantum group, which is similar to a quantum group but using.
Okay, so Momole, you said? I don't know it. But does it provide? Is it a Hopf algebra? I mean, so this is the future directions. yeah, so I would like to know, but this is exactly what I mean by future directions. As soon as you say that word, there's a quantum symmetric group. There's a lot of questions that come up, and I have not looked at them.
The reason you were asked so many questions about Kronecker program was the GCT program was at the time.
Okay. Anyway, so this is I just started this in February, but it's nonetheless quite interesting. So this is the Kronecker problem. This is the Littlewood-Richardson coefficients, which we've already done. This is the Littlewood-Richardson rule, which I've written there. Okay, so this is our examples of crystals. So the first one is, this is a GLN crystal. This is all GLN here. And that is a column strict tableau. These are the column strict tableau of this shape. Column strict tableau, column strict tableau, column strict tableau. And you organize them in a graph so that there are edges, F1 tilde, F2 tilde. This is the crystal of the adjoint representation of SL3 or GL3. And these are how you normally label the weights of this crystal. And up at the top of this crystal, there's a highest weight. And that's what we mean here by this highest weight in this picture. So this is what a crystal looks like to me. All right. So I said, do I have any feel for what a crystal for the symmetric group should look like? So here's an example. These are the standard tableau of shape of this shape. So maybe I should draw them just so that I don't go too fast. I mean, the first one is the column reading tableau. Just read down the columns. And then you try to switch two entries in this, and you put a little ledge according to which entries were switched. And then you switch two entries, and you put a little edge. And you switch two entries, and you put a little edge, labeled edge. 1, 2, 3, 4, 5. Oops, something happened there. No, that's right. And S4 tilde, and 1, 3, 2, 4, 5, and then. And now you can see, all right, this wasn't so bad. This kind of does look like a crystal. And this thing up here, this kind of looks like a highest weight. And if you think about it a little bit longer, then you know from the theory of Murphy elements or something, there are weights here. These are the contents of the boxes. So content of 1, content of 2, content of 3 is -2, content of 4. So you could make weights and crystals and a highest weight, and it seems like, okay, everything's working. That wasn't very hard. All right? Okay. Great. So now this is the setup. Let me write this one because this is important. So the problem is that you need to make a tensor category. And in fact, let's call this some theory of graph categorification. So actually I have not, that's another theory that I haven't really kept track of, is the tensor category, fusion category, classification type theory. But that's what we want. We want some category of graphs, so certain graphs, and we want that category to have, so direct sum should be, is disjoint union in the world of graphs. So we want this to be a subcategory of some category of labeled graphs. So disjoint union, and we want some simple objects. Well, we want the simple objects to be these Bn lambda. So this over here was B5, 2, 2, 1. So we want some Bn lambda for partitions of n. And we want these to be the connected objects, the connected graphs in this category Bn. So we want a graph category. But more than that, we want, so we would like the dimension of Sn lambda to be the cardinality of Bn lambda. So if you take the simple crystal corresponding to the simple representation, you would like the cardinality, the number of vertices, to be the dimension of the module that you're trying to construct. And then you would like, so the most important feature somehow is that this graph category that I'm building, I want it to be monoidal. So I want a monoidal category, which means that you have to tell me how to take the tensor product of two labeled graphs. So in practice, that means you have to take Bn mu, tensor Bn nu. Tensor just means cross product of two graphs. The set is just the cross product set. And you need to make that into a labeled graph. So I don't know what this category is, but you in such a way that you can pick out the connected components and get the connected components to spit out these numbers, gamma, mu, nu, lambda. Or if you had a way of doing a computation to decompose this graph into connected components, then you would be able to compute these by this kind of a statement. But a very important thing, and I'm going to come back to this repeatedly, is that you need associativity in this family of functors. So in this family of maps. All right. And then, of course, on the Grothendieck group level, Grothendieck ring, I should say, ring. So once I have a tensor category like this, I can make a Grothendieck ring of that. And I want that to be isomorphic to the Grothendieck ring of SN modules, but just by sending the class, the isomorphism class of this simple object to the isomorphism class of this simple object. That's somehow the goal. So I actually played with these crystals for quite a while before I sort of wrote down axiomatics like this. So that's the monoidal structure. And then after I played with them long enough and I wrote down axiomatics, started to get it organized, what has to happen, I proved it does not exist. These axioms are too tight. All right? If you want this cardinality to be the same as the dimension, give it up. It's not going to happen. And I should have maybe just quit there. Except that I had done all these calculations before I realized that it doesn't exist, and so I didn't quit there. Let's see how we're going on time. I end at 10:20. Is that right? Okay. So I might tell me with the slides. Tell me if I'm going too fast because I'm sort of not writing things. Okay. So first of all, this for n equal 1 and n equal 2, it's quite easy to show that it exists and it's what you think it is. Now, to be honest, I have not written down the details for n strictly greater than 3. I have written down very carefully n equal 3, and it does not exist for n equal 3. And then I said, well, I've got to be able to jack it up somehow. So this is a little bit of a lie in terms of my writing. But let me just give you an example of how you prove that this doesn't exist. So this is the tensor product rule for the symmetric group S3. All right, so this guy is the trivial representation. And of course, the trivial tensor with anything is just the same. Trivial tensor A is A. And the sign conjugates, so the sign tensor the trivial is the sign. The sign tensor this is the conjugate of that hook, which is the sign tensor this is the conjugate. So this gives us a trivial back. And so the interesting stuff for this category is in the product for this. This is a little rank 3 fusion type rule. It's not modular, I don't think. But this is the non-trivial component right here in the middle. Okay, so if you think about these axioms, what I need is the following setup. I'm going to let A be the symbol 1, 2, 3, because that's, so maybe we should write that. So Bn, B3 of this guy is just one standard tableau. It's a graph with just one vertex. B of this guy is 2 standard tableaux, which are connected by an edge labeled S2 tilde. So that's a little graph that looks kind of like this. And B3111 is just 1 standard tableau. So again, that's just a graph with 1 vertex. But somehow it's important that these 2 vertices are different color, because one is the sign vertex and the other is the trivial vertex. All right, anyway, up here I've just labeled them as A, B, C, and D. And I have to produce a tensor product rule for the A, B, C, and D. That's what this says. I have to produce some kind of tensor product rule so that 2 things happen. First of all, I want it to be some expansion of this picture. And that means that this internal box here needs to be a permutation of A, B, C, and D, so that it will have 1 trivial component, A is the trivial, 1 sign component, D is the sign, and BC is the component corresponding to the hook. So that's what I want in the middle. And these 2 guys, they have to be a copy of the sign representation. So somehow I need to put B and C into these 2 boxes, B and C into these 2 boxes, and A, B, C, and D into these 2 boxes, and I need associativity. And you need associativity if you want your Schoenstedt to work. Okay, now I've set it up for you. You can prove it yourself. You check if you're really disorganized, you check 2 times 2 times 24 cases, so that's whatever it is, and they're all bad. But you can be more organized than that. It's not so impossible. Okay, so this is not going to work, and we should give it up maybe. However, once you start to play with it for a while, you try to do it anyway, you realize that this might be the axiom that's broken. If I could give up on this, not requiring the graph to have the same number of vertices as the module, maybe it might work. And in fact, that's really strongly indicated by the issue of stability. So stability says, and stability is an old statement. I believe it's due to Murnaghan, at least that was where I learned it. One I just want to mention, because there's a beautiful paper of Briand, which hasn't been read enough by our community in this game, and I just got it out again 2 days ago, and it's really wonderful. So we should learn more about it. But stability says that if you have a partition, lambda 1, lambda 2, etc., then you let lambda bar be everything but the first row. And the idea is that you could reconstruct lambda, you could reconstruct the first row if you knew what n was. If you know that n is 37, and I tell you all the other rows, well, then the total number of boxes has to be 37, so you can reconstruct lambda 1. Okay, so then stability says that as long as n is larger than 2 mu 2 plus nu 2, then this coefficient, this Kronecker coefficient, depends only on mu bar, nu bar, lambda bar. And so we can call that stable coefficient, we'll call that stable coefficient phi mu bar, nu bar, lambda bar. Okay, so it means that we should look at these b and lambda as n gets large. So I have all these graphs of my simple modules, and we should look at them as n grows. And how did I Yeah. So the first one is, it becomes clear that B infinity empty. So I'm ignoring the first row now. So let's just do an example to make. Suppose I said B7 and the second row is empty. Well, that means that the first row has 7 boxes. Well, there's only one standard tableau for that guy. So this graph is just a dot, just one vertex. So, and if this was 70, it would be the same, just one standard tableau. So you can see that it's stable. So this is just a dot. Okay. Similarly, I think that picture up there, it's if you started with a little hook, then the first operation you can do is S2 tilde, and that gives you 1, 3, 2, 4, 5. And then the next operation you can do is S3 tilde, which switches the 3 and the 4. That gives you 1, 2, 3, 5, 4, and so on. And you see that B infinity box, because once you remove the first row, you just have a box, is a graph that looks like this. All right, you with me so far? I'm just creating stability. And so the next one is B infinity, say, like this, and this will be some graph like this. I think, I must have been, hopefully I was organized enough to, yeah. So here you can see I actually computed it. I started with the column reading tableau. The column reading tableau is the highest weight. And then I applied a transformation and I got this string. You see that corner box there? So in fact, I'm going to define the dimension of B infinity lambda bar to be the number of boxes of lambda bar, and the directions, this maybe I should call it infinite directions of B infinity lambda bar, to be the number of removable boxes of lambda bar. So you can see here that this corner box here causes an infinite chain going off to the right. And if you add a little more to this, the same corner box still causes an infinite chain going off to the right. And if you put the next bit in, the same corner box still causes an infinite chain going off to the right. And so the shape of this crystal is like this, but it extends infinitely in one direction because there's one corner box. So these I believe are going to be some important data about these crystals. All right, and then for this guy, I want to put these on the board because they're going to. So this guy, we get a picture that looks like this. All right, so it's just like the previous one, except it has this extra thing coming off the front, and you can see that here. When I build the crystal, I physically built it, and you can see that it produces a picture like this. All right. So now I have shapes like this. These are the shapes. These are my new crystals, and my new crystals have an infinite number of vertices. And I have to say that I was already thought that was a good thing, because if we go back to this fusion rule, oh, I hate when people do this. Yeah, when we go back to this fusion rule, this looks like fusion for vertex algebras. So if you study W algebras or something and you get fusion, you get rules like this, and all of those modules are infinite dimensional. So when I saw infinite dimensional models producing me fusion categories, or close to fusion categories, that for me was a positive thing. Okay, so now I have a new class of graphs like this. And so now the problem changes, and the problem is, let's now make a so make a category B infinity. So the simple objects are still graphs. We want them to be graphs, but they should be some sort of B infinity lambda bar, where lambda bar is now, I think of it as all but the first row. And I want to make it monoidal, so make a graphical tensor category. And you want this so that you can use it to compute just these stable numbers. All right? And then, as people are observing in a different language, what is natural to define, because I'll say, there is to define some functors from this category to these finite categories that don't exist, but we want to define some kind of a thing, and use these to compute then oops, sorry, this is, what did I call it? Phi or phi? So these stable things are phi, and then use these to compute the non-stable ones. And there's really good reasons to do this, because stability has been sort of in our minds has grown in such a wonderful way from the theory of FI modules, from the work of Sam and Snowden. So I don't know how many names I want to put here, but there are lots of them, and they're beautiful works. So Church, Ellenberg, Farb. We are learning a lot about stability in representation theory through this kind of work. But I just stole this from Ina's talk last week. So Ina gave a beautiful talk where she explained these functors on the corresponding representation category of S infinity and the representation category of Bn of Sn. And so we're just trying to make the crystal theory mimic the representation theory as it should. So this is somehow the idea of how you should work with infinite tensor categories. Okay, so that's what I've said there. Oh, maybe I'm going faster than I expected. Okay, well, that's good, I suppose. Any questions so far? All right. So I don't know. I don't yet know this tensor product rule, and I have not yet proved that this category doesn't exist either. So it's open. It's a future direction, and I think. All right. So. I should say, maybe because there should be questions, this category is not, so Bn, let me make a remark that way. This KB infinity should be isomorphic to the Grothendieck ring of S infinity modules, or the rep ST, where T is, so this is Deline's category ST. So that's what's in our head when we try to build this categorification. Now these categories are not semi-simple, and so you might complain that isn't the graph category semi-simple? And my answer to that is no. If you use directed graphs, it's not semi-simple. Yes, but when T, is an integer, it's not, right? So, yes. But this, the point is that this picture has a subgraph here. This is an extension between this object and this object. Which is part of the reason that I want to sort of, I have been wanting to make my graphs directed, even though they didn't yet have a right to be. All right, so that's just a remark there. Okay, so I want to now talk about Halverson Lewandowski. Halverson Lewandowski. Because this is an idea that this was my first response, is that crystal theory for symmetric groups has to work because it's already in the literature. So let me explain. All right. So this is something we all recognize, I think, is that V tensor K is isomorphic to the direct sum over lambda partitions of K, such that lambda n plus 1 is equal to 0, where you take ln lambda tensor sk lambda, and this is a simple sk module, and this is a simple gln module. All right, so that's Schur-Weil duality. Schur-Weil. And there is a crystal version of this. So the crystal version, and this will explain some of my comments before about Schoenstedt, and that is that let's just take words of length k in the alphabet 1, 2, up to n. And there's a bijection, a very famous bijection called Robinson-Schoenstedt-Knuth, which says that this is the disjoint union over lambda partitions of k, lambda n plus 1 equals 0, of Bn lambda. Remember, that's the crystal, the GLN crystal, tensor Bk lambda. That's the symmetric group crystal that I want, the irreducible one. And this bijection takes a word, I1 up to Ik, and it sends it to a pair, PQ, where Q is a standard tableau, standard shaped lambda, and this is a column strict tableau, shaped lambda. And it was recognized very early in the theory of crystals that this is a crystal isomorphism, at least as GLN crystals. And then you have to decide a little bit what you mean by an SK crystal on this side. And actually, again, in the spirit of future directions, I think one of the smartest answers to what kind of crystal this is to use cactus action, the cactus. But if you don't know cactuses, ignore that remark. So I do think that perhaps in the future directions that cactus actions are going to have a chance of producing some sort of S-symmetric group crystals. Anyway, this bijection then allows you to pick up the crystal structure for each one of these GLN crystals just by knowing the crystal structure on words. All right, so what was my comment at the beginning? And that is that Halverson Lewandowski say that if you take the same V tensor K, so V here is n-dimensional space, and you view it as a symmetric group cross cross partition algebra module. So then that decomposes as a direct sum of partitions of n now, with lambda bar less than or equal to k, and here we have the symmetric group module indexed by lambda, and here we have a partition algebra module indexed by lambda. And the crystal version, so maybe I put it this time with a question mark version, is a bijection from the left-hand side. So the left-hand side, again, is words of length k from the same set, 1, 2, up to n. And the right-hand side, so this is the Halverson-Lewandowski bijection, is a disjoint union over partitions of Bn lambda, so the symmetric group crystal, so standard tableau, cross some other partition algebra like crystal. I only know this on the level of sets. So this is I1, I2. So some word goes to a pair, xy, where x is a standard tableau, standard, shape lambda. And this y is what you would call maybe an add-remove sequence, remove of length k, ending in lambda. Or you could, if you know Bernoulli diagrams, it's a path in the Bernoulli diagram to lambda, in the partition algebra Bernoulli diagram. So they have a bijection. It just physically does this. It physically does what Schoenstedt does, except for symmetric groups. All right. So what's wrong with this bijection? So that was my first comment, is it has to work. It's already in the literature. You just have to unwind it. You have to figure out, why does this tell you what the theory of crystals is? And the reason it doesn't work is because this bijection does not satisfy associativity. So all right, so it doesn't, what you want, that if you inserted some word and then moved that word over 17 spots, and then, so I don't know how to, you want the answer of this bijection to respect all the decompositions that associativity would give you, and this doesn't satisfy them. All right, so that's not a very good explanation, but believe me, the associativity breaks. The problem is that this is not quite right. Okay, otherwise it would solve the problem right there. No, PKN lambda, this means the irreducible module for the partition algebra indexed by lambda. So this is the partition algebra. And this is the simple PKN module. So PKN is the centralizer. So PKN, surjects onto the centralizer of the symmetric group action on V tensor K. So, all right. Okay. So this is what we've written already. Okay, so I want to do, I hope you're still following, because I've gone much faster than I expected, but it gives me time to do these examples. So this example here is k equal 2. So I'm just going to do Halverson-Lewandowski. Let me. Write it here. So this is k equal 2, n equals 6. So I have words of length 2 from the set 1, 2, up to 6. And I'm supposed to produce from that some crystal bijection. So I just physically did what they told me to do, and I looked at the components, the connected components that we get. And you find, so this is the decomposition that you should get in symmetric groups, is that V tensor V is 2 copies of the trivial, 3 copies of the hook with 1 box in the second row, S copies with 2 boxes in the, 1 copy with 2 boxes in the second row, and 1 copy with, so those are exactly these crystals here. All right? So what you have to do is you have to put 2 copies of this graph, 3 copies of this graph, 1 copy of each of these 2, and fill up that square. All right, so this is a geometry problem now. And then you fill it up somehow, and then I'm going to start asking you, so in tensor products V tensor V, you don't see associativity. But when I get to V tensor V, I'm going to ask you, is associativity holding as well? So here, but let's just do it for this case. So these are the 3 copies of this line in Halverson, Low, and Dorsky. This is the copy of this crystal down here. You can see it's got an extra edge sticking up out of this staircase. That's this crystal down here. And then I have a copy, a funny embedding of this crystal here in there. They chose to embed it in some kind of crazy way. And then, and then these 2 down here, those are the copies of the trivial, all just 1 vertex by itself. Okay, so when I actually looked at Halverson, Low, and Dorsky, well, it was disturbing. First of all, this doesn't satisfy good stability, right? At least not face up. If you let 6 get large, well, maybe it does, but you worry. Second of all, it doesn't look so symmetric. So I said, well, how about this? I can embed this sort of a slightly better way. All right, so I felt good about that. And it's interesting because these graphs, if you read around the border here, you get the stable decomposition. This stuff down here is kind of weird, but this stuff around the border is always nice. Okay, so then I did V tensor 3. So then I did k equal 3. V tensor V. And in fact, V is, so this is 5 copies of the trivial plus 10 copies of this guy, n large, I don't know, plus 6 copies of this one, plus 6 copies of this one, plus 1 copy of the column, plus 1 copy of the little hook, plus 1 copy of this guy. So those are the components, and you have to try to fit them into a cube. All right. Now I have to admit that in this picture I cheated. So V is equal to 1 copy of the trivial plus 1 copy of the box. That's the reflection representation. This is the permutation representation, and there's a trivial there. So in fact, this picture is only Bn box tensor Bn box tensor Bn box. And this picture is only the stable part. So this is just like in the previous picture. I said if we go around this boundary, you see the stable part. Well, this is the boundary of a 7 cube or a 6 cube. All right? So I'm only looking at the stable part. And this is tough. You've got all these components, and you need to fit them all together to form a cube. And you want stability, and you want associativity. And this seems to be, you see there's 3 copies of this. Oh, there's a mistake there. That should be also 1 more trivial. So this edge shouldn't be there, sorry. So there's 3 copies of this trivial in a symmetric kind of a way. These 2 blue copies, that's all 1 crystal. are symmetric. And this copy of a crystal like this and this copy of a crystal sort of like this are on opposite sides. So this is as close to associativity as you can possibly get in V tensor V tensor V. And it seems, so I have no, it seems to be a miracle that around the boundary, around the stable region, it works. As you go down towards the origin, towards when n is small, you always see what I would like to call singularities. All right? So this problem has turned, so this is the most fascinating thing to me of all, is that this Kronecker problem for me has now turned into a geometry problem, where I have affine space of some dimension, in this case 3-dimensional affine space, and I have to decompose that into large pieces. So dimension is the number of boxes of lambda. So I have some big open cells, and then on the boundary of those big open cells are some lower dimensional faces, and then on the boundary of those lower dimensional faces are some even lower dimensional faces. And there's lots of singularities around the origin. The origin is really yucky. I don't have any way to characterize the origin. Okay, I think I stopped there.
So you do the 9-dimensional cell or 10-dimensional? The north, west?
So this cell is 3. Oops, there should be a 2 here. Sorry, there should be a 2 here. So these are 3-dimensional cells, and we're seeing only a 2-dimensional image of each of those. So this is one copy of this guy. This is one copy of this guy. This is one copy of this guy, and this is one copy of this guy. Those are all 3-dimensional pieces. They look like big tetrahedra, and I'm only looking at a 2-dimensional face. I'm only looking at the boundary, which is 2-dimensional, you can see here. These guys, these red ones, are these type of components. So these are actually 2-dimensional components, but because I'm looking at the boundary, I only see, because I'm looking at this shell, I only see 1 dimension of it. And these, they look 0-dimensional here, but they're in fact 1-dimensional because I'm looking only at the. So these you don't see. These always happen down at the singularities, because as soon as the trivial appears, then it won't appear again stably. So if you're only looking far out, you won't see these trivials. Yeah. Yeah.
So this stability that you're using is the one that comes from the partition algebra, if you like, and it's the one that inner uses. So inner uses the partition algebra to prove about these categories and things. But there's now a whole chuckload of other stabilities coming from, I think, Sam and Stanbridge and all that work. Do you think that this stability is special? The partition algebra is special?
No, I should say I don't know. I'm vaguely aware of other stabilities, but I haven't studied them to feel like I know whether they're related or just constant. I'm not qualified yet enough to say what they are. I can say that I sort of felt like they were sort of all the same stability packaged in different ways, but I don't actually know if that's true, or if I can justify that. Yeah.
And, sorry, in this picture, your origin is not trivial in the middle?
No, my origin is way down at the opposite end of this corner, so it's way down in the cube. This is, I've got a cube, and I'm just looking at the outside face, the outside of it. So the origin is way on the internal corner. You don't see that at all in this picture. Yeah.
One quick question, I guess. You talked about thought to have associators?
Yeah, I wondered about, so I did say, I mean, Steve has been with me in Melbourne, and I'm always talking about, oh, well, there might be a non-trivial associator, or there might be but, I mean, when you're trying to do combinatorial calculations, in a sense, there's too much freedom. I think that's been the problem all along with this problem, is that there's too much freedom, and you need to find where the rigidity is. So I don't, so it has now become clear to me that if you put too much rigidity, then it just breaks and your category doesn't exist. So I've just been sort of working from both ends at once, and I've been using trivial associators for the moment because I don't know how to guess. I don't have any other structure to guess a better associator.
Sorry, was the take-home message supposed to be that there is hope for the stable Kronecker coefficients then? That there'd be crystals? Or you are hopeful? Or you just haven't?
Well, okay, so the final end, in the end of all of this, so now I have been actually sort of looking at it for 6 or 7 months, and I'm not convinced that we as a community really know much more than Littlewood and so on did. However, we have really good points of view now that we didn't have before. So stability is one of them, the FI models. That's a partition algebra is another one that we just didn't have it in 1986 when I was last looking at the problem, and now we have this kind of stuff. And so I'm quite confident that those points of view are going to help us get our heads around what's easy and what's hard. But I don't know. This point of view is what I want to offer as something new. I have never seen a geometric perspective to the problem before. Well, that wasn't just stolen from GLN. I mean, Brion's paper has global sections of line bundles for G mod B. But this kind of geometric idea where you have some moduli space and you're trying to compactify that moduli space and it's got a nice stratification, that I had never seen in this context. And these computations really indicate that. So I'm hoping that that's another new perspective.
And so, would you say that certain crystals, do you think of them as a Lie algebra thing, or do you think of them as a group thing? Because obviously, like the symmetric group.
No, I think of them as a graph categorification problem.